This video is a crash course of each of the topics of Unit 3. So starting with day 1. The first thing we talked about is when a rational expression, which is really just another name for a fraction, is undefined. Undefined just means the denominator would go to 0. So for example, if I set the denominator equal to 0 and 5 over x would equal 0. If I set it equal to 0 in the next example and solved, x would equal 6. So what that means is that you can plug any value for x into this expression 5 over x except for 0, because if you did that, you would get 5 over 0 and you can't divide by 0. Same idea over here. X can't be 6 because as soon as you plug it in, you would get 6 minus 6, which would then make it be over 0. So what I'm solving for in the denominator is just for what values of x the entire denominator would go to 0. So for harder examples like 4, I would factor this to solve it, and I would get 2 values out of it. So what that means is I can pick any value of x except for -3 and -4, because if I plugged them back in, the denominator would go to 0. The next thing we talked about is simplifying. So actually, I'm going to ignore this question. Let's just talk about simplifying fractions in general. If I asked you to do 2 divided by 2, you would say that's equal to 1. If I asked you to do 10 divided by 2, you would say that's 5. But let's talk about why it's 5. 10 is broken up into 5 times 2. And if you ignore the 5, 2 divided by 2, we already said that was 1. So I cross it off because I think to myself, that's reducing to 1, and 5 times 1 is 5, and that's why the answer is true. If I asked you to do 15 over 20, with this same process, I can break up 15 into 3 times 5. And I can break up 20 into 4 times 5. 5 divided by 5 goes to 1, and that leaves me with 3/4. So I've started with the basics of numbers to show you that I'm breaking up each of these numerators into factors, which implies that we are using multiplication. Okay, that's a multiplication symbol. That's a multiplication symbol. So if I can break it up into multiplication and then I see things that are alike, I can cancel those out, which canceling just means reducing to 1. So in this blank down here with simplifying rationals, it says when can you cancel? The answer would be when multiplication is involved. So for the first example, I have 2x over x. That's multiplication, so I can cancel the x's. That leaves me with 2. If I actually added another example here and say x over 2x, I can cancel 1x in the top with 1 in the bottom, but remember it's reducing to 1, so that's 1 over 2 as a final answer. If you look at B, anytime you see a plus sign, I want you to think that those terms are glued together. They cannot be broken up. And the plus sign is not multiplication, so I cannot cancel those 10s. So this actually can't be simplified any further. And if you ever have any doubts about why I can't simplify it further, think about this. If I did 2 plus 10 over 10, I just picked a value of x. That would be 12 divided by 10, which is equal to 1.2. If you tried to cancel these 10s, like some students try to do, that would give you 2 plus 1, which would give you 3, and that's not equivalent. That's not mathematically sound. So that's why you can't cancel these 10s. Again, it's because of that addition, or sometimes it's subtraction. So same idea in C. There's addition. I can't cancel that or reduce that any further. So I actually add little no's here. Can't reduce. Now for D, again, plus sign. These terms are married together. Now, I actually do this off to the side up here, because I should have emphasized this more. If you have anything over itself, it's equal to 1, even if it's a binomial. So x plus 2 over x plus 2, it's the same thing. I can reduce those to 1, which then leaves me with x plus 1. So I'm canceling because there's multiplication going on in between each of those factors. E, these are exactly the same, even though they're in a different order. Addition's commutative, so that would reduce to 1. F, I can't reduce any further. These are glued together. You can't cancel those 12s. And lastly, G, there's multiplication in the top, there's multiplication in the bottom, so I can reduce the 4 with the 12 and get a 3, and that would reduce to 3x over x minus 1. So that's how we reduce those, or that's how we simplify rational expressions. When we can, when we can't. So what we're going to do then is also look at other special factors. So I just said that if you have things that are exactly the same, but switched with addition, that's just equal to 1 because addition is commutative. But if they're the exact opposite with subtraction, it's actually going to equal -1. Pick any two numbers. If I had 9 minus 8 over 8 minus 9 to represent A and B, 9 minus 8 is 1. 8 minus 9 is -1. That reduces to -1. So no matter what A and B are, it's going to reduce to -1. So for example here, these are exact opposites with subtraction, so I know right away those equal -1. Okay, so I'm going to look at this first example, and I notice that I have a monomial and a monomial. I can reduce, everything's being multiplied, so I can reduce the 5 with the 10 and get a 2. An x with an x squared and leave an x. Y squared with a y to the 12th, and that leaves me with a y to the 6th. So this is 2x y to the 6th, and all over 1 because everything canceled, and that would be our answer. Exact opposites with subtraction, that's a -1. And then for 10, I'm going to factor this first, just like how when I had 10 divided by 2 and I rewrote it as its factors so that I could see what's the same to cancel it. I'm going to factor a 2 out of the numerator. Oops. And look at the denominator as well. These are, sorry about that. These are opposite factors, which means I can reduce them to -1. -1 times 2 is -2. Coming down to 11, again, I'm going to factor this. So I'm going to factor anywhere I can to see what it's made up of. I see the d minus 3's are the same, so I can cancel the d minus 3's, and that leaves me with 5 over d. And that's the general idea of simplifying. So we factor first when we can, and we then cancel like terms. So day 2 is really more of the same, it's just harder factoring problems. So again, this is factor first, then we simplify or cancel, and just make sure we're always in lowest terms. So for example, I'm going to skip ahead, let's look at 2. The numerator here, this is 3 terms, leading coefficient of 1, so this is an add multiplies factoring. So I can cancel the x plus 4's, and that leaves me with an answer of x plus 7. For 4, the top is 2 terms, but they look like perfect cubes. So this is soap. The bottom is dots. So recognizing factoring is going to be important in this unit. Okay, so I took the cube roots, same opposite, always positive, square product square, all over. Dots is a plus 1, a minus 1. I can cancel out the a plus 1's, and essentially this is what I would then have left over as my answer. Something like 7, top is dots. Bottom is just y minus 9 times y minus 9, so I'll write that out twice. My y minus 9's would cancel. It's only 1 in the numerator and 1 in the denominator, because those reduce to 1, and that leaves me with y plus 9 over y minus 9. You cannot reduce that further. Lastly here for 9, just to throw a different type of factoring there, it has 4 terms, so that means I'm probably going to do factor by grouping. So I can factor out an x squared from the first 2 terms. I can factor out a 4 from the next 2 terms. So that factors to x squared plus 4 times x minus 5, so that would be my numerator, all over, and then I can pull out a GCF in the denominator. Whatever's alike, I can cancel out. And that leaves me with x squared plus 4 over x. Do not cancel those x's because that x squared is glued to that 4 or married to that 4 with the addition sign. So you don't want to break those up. So then we worked into multiplication problems, which really are just bigger reducing problems. You always look to factor first, and then you cancel one factor in the numerator with one in the denominator. And you can do this anywhere in the problem. So let's actually start with something like 3, and then I'll work back to the monomials. For 3, I factor where I can. So this is x minus 2 all over factors of negative 2 that sum to 1 are 2 and negative 1 times factoring the other numerator. This goes to x minus 2, x minus 1 all over x plus 2. Now, anywhere in the problem, I'm looking for a numerator with a denominator that'll cancel. So, for example, I have one denominator of x minus 1, one numerator of x minus 1. Those together reduce to 1. And then I've got... Actually, that's it. I can't cancel anything else. There's no more matching pairs between a numerator and denominator. I'm recognizing I have x minus 2, x minus 2. So that's x minus 2 squared all over x plus 2 times x plus 2, which is x plus 2 squared. That's done. You can't reduce that any further. For 4, I can factor the numerator as a plus 3, a plus 3. The denominator is dots. Numerator of the next one is just a GCF, and denominator is already factored as a plus 3. Now that everything's factored, which means there's multiplication between all the terms, I look for numerators with denominators. So as you guys are seeing, everything is canceling out except for 3. So my final answer is just 3 over 1, which is just 3. So I skipped over the first 2 because I say factor everything first, and then the first example doesn't factor. So sometimes I'm going to give you stuff that doesn't factor. These are monomials. There's no addition sign, so nothing's going to factor out of them. But it works similarly to the ones that I just did, in that anywhere in the problem, I can reduce stuff that I know will go to 1. So for example, I know I can cancel an x with an x. Those will disappear. I can cancel an a with an a in the numerator. I can cancel these 3 b's in the bottom with 3 in the top. I can cancel the 3 with the 27 to get a 9. I'm just doing some reducing here. And then I can cancel the 9 to 1 and with the 18 to get a 2. Let me just zoom in here so you guys see what I didn't cross off. In the numerator, I still have a 2, an a, and a b. In the denominator, I have a 5, and that's it. Everything else canceled. So my answer is 2ab all over 5. And then I can do the same thing over here at 2. I'll actually rewrite this. This is still 6a to the 5th, x to the 12th, all over. Whoops. 4y squared, because I multiplied that out, times 4y to the 4th, all over. 3 cubed is 27, a cubed, x cubed. Now I look to cancel stuff. So I can cancel the y squared, the y to the 4th, but that would leave me with a y squared. I can cancel the 4's. I can cancel the a to the 3rds but that would leave me with an a squared. I can cancel all my x cubes, but that would leave me with x to the 9th. And then I can reduce the 6 by 3 to give me 2, and the 27 by 3 to give me 9. So let's see what I have left over here. I've got a 2a squared, x to the 9th, and a y squared. So that's my numerator. All over just 9. That's all I have left over. And that would be my answer. Okay. So once you know how to do multiplication, that's the general idea, you can do division. Keep in mind that division is the same thing as multiplication. I can say 10 divided by 2 is the same thing as 10 times 1/2. This is where they told you in younger grades to do keep, change, flip. You keep the first, you change the sign to multiplication, so that's where this is coming from, and then this is the flip of 2. Okay, so this is keep, change, flip, and we'll factor 2. So for example, I can look at number 1 and think of this as 6x over 4x minus 16 times x squared minus 16 over 4x. I did keep, change, flip because I flipped that second fraction after changing the sign to multiplication, and then I can go ahead and factor. Okay, I look for things that are alike that I can cancel. So I can cancel these x's, I can cancel the x minus 4 with the x minus 4, and I can even reduce the 4 with the 6 by dividing each of those by 2. So here's what I have left over. I've got a 3 and x plus 4, and then the denominator I have 2 times 4. So 3 times x plus 4, you can leave it just like that, don't bother distributing, and then 2 times 4 is 8. That would be your final answer. Okay, I'll do 4 next. So again, keep, change, flip, and I'll actually factor while I do this. So like in the numerator of the first fraction, I can pull out an a squared. In the denominator, that looks like dots. Times. So now in the numerator, it's this 3ab plus b squared. I can pull a b out of each of those. In the bottom, it's now 16a squared minus b squared, which looks like dots. So now I go through and look for things to cancel that are the same. And that looks like it. So here's what I have left over. And that's division. So really division is just multiplication. You just have to rewrite the problem. All right, so now we get into some harder problems. And I know this seems silly, but adding and subtracting fractions are harder types of problems because you need a common denominator. Remember that if you have common denominators here like 7, 1/7 plus 4/7 is just 5/7. It's the same idea with variables. You're going to keep the base, add the numerators. So this first day was really just keeping everything consistent with denominators. So I already have a common denominator. 3 plus 5 is 8. And then I can reduce this. So that equals 2 over y. Down here at 3, I can subtract them as well. Just make sure you keep in mind this subtraction is going to distribute to the entire binomial of the second fraction. So this is 4b minus b minus 6 all over 5 minus 10. Oops, 5b minus 10. 4b minus b gives me 3b. So 3b minus 6 over 5b minus 10, and then I can factor. Sorry, that says b minus 2. And then I notice the b minus 2's are the same, so I can cancel those. And that leaves me with 3/5. Okay. I can do, scrolling on down, something like 5, where I'm again distributing that negative all the way through. And then I'm actually going to clean that up before I even go further to write the whole fraction. +1, -1, those will go up, disappear. So this leaves me with c squared d. Stop it. C squared d minus cd squared all over c squared minus d squared. And then I factor to see if I can get stuff to cancel. So in the numerator, I can pull out a CD as a GCF. In the bottom, that's dots. The C minus D's will cancel, and that leaves me with CD over C plus D, and you're done. You cannot reduce that any further. And again, that's because of that addition sign in the bottom. All right, keep scrolling. Okay, so then we changed it the next day to unlike denominators. It's just like when you did 1/5 plus 2/15. You decided on what we called the lowest common denominator. So in this case, 15, and I would have to manipulate the first fraction to rewrite it before I could add it. So 3 plus 2 is 5 over 15. We look to reduce, goes to 1/3. Same concept here. So like if I look at number 1, my LCD would be 6 between 3 and 2, and that's really just the lowest common multiple. So that means I multiply the first fraction by 2 over 2, and the second fraction by 3 over 3. So then I do 8 plus 15, which is 23. So 23x over 6. And I can't reduce 23 with 6, so you're done. For number 2, the common denominator I would pick is x cubed, because I can turn the x squared into an x cubed by multiplying it by x. So this reduces to 4y minus 2xy all over x cubed. And I can factor that numerator. I actually can pull out a 2y. But even with factoring it out, that's not going to reduce. So that's just your final answer. For 3, I would pick an LCD of 10x, because ignoring the x's, between 5 and 10, I would pick 10, because I can turn 5 into a 10 by multiplying by 2, and each of them already has an x. So that gives me 6 over 10x minus 7 over 10x, which is 1 over 10x. For 5, the LCD would be, again, it's really the highest powers that I'm looking at. So I would say a squared and b squared. So I can multiply the first fraction by a b, the second fraction by an a. So ab plus b squared, because I have to distribute that to each of those, plus a squared minus ab. And this is all over our new common denominator, assuming I wrote this as one fraction. a squared b squared. And then I'll clean this up. Keep in mind, oopsies, all over a squared b squared. Now keep in mind, these terms in the numerator with the plus sign are glued together. So I cannot cancel those with the a squared b squareds in the bottom. All right, keep moving on. So gradually, again, it's still the same process here, but the denominators I'm just making a little bit more complicated. So for number 1, I'm going to look at my denominators and actually factor them first so that I can see what they're made up of. In doing so, it allows me to say that my lowest common denominator would be an x and an x minus 1. So I'm really taking one of each of the factors in the bottom that I'm seeing. So this second fraction already has the common denominator, but the first one would need one. We need an x. So in doing so, x times x plus 5 is x squared plus 5x, and then minus 6, all over our new common denominator, x times x minus 1. I'm going to factor this. Factors of negative 6 that sum to 5 would be 6 and negative 1. X minus 1's cancel, and this leaves me with x plus 6 over x. Now, number 2, actually, no, not number 2. I'm not going to do that one. I'm going to do number 8. Let's look at number 8. So what I want you guys to notice is that I have 4 minus m and m minus 4. Those are really similar, but not quite the same. What I'm actually going to do is multiply the top and bottom by negative 1, because in doing so, I'll do this off to the side. 4 minus m times negative 1 gives me negative 4 plus m, which is the same thing as m minus 4. So in doing that, I actually can rearrange this to now look the same. M minus a negative, m minus a negative goes to plus, so this goes to m plus 3 over m minus 4. Scrolling back up, so now looking at 6, I'll factor that denominator. I notice that the other fraction has an x plus 6, but needs an x minus 6, so I'll tack that on there. So I have 7x plus 3 plus, and I do have to multiply this all out, x squared minus 5x minus 6, all over our new denominator, x plus 6, x minus 6. And now I'll just clean this up. All right, so I added this, right? Okay, so I've got x squared plus 2x minus 3. That actually does factor x plus 3, x minus 1, if you wanted to factor that numerator, but nothing will actually cancel after that, so you're done. Now for number 7, I don't have to factor the denominators, but I can see that they're different, so I'm going to want one of each of those. So like the first fraction is going to need an x minus 5. The second fraction is going to need an x plus 5. So when I distribute, this gives me 2x minus 10. Now keep in mind this is really a negative 3 that's distributing through. So this is negative 3x minus 15. And if I clean that up a little bit, 2x minus 3x is negative 1x minus 25 all over x plus 5, x minus 5. That's the common denominator. This was just my work for the numerator from that. All right, and then just reminding you again of what we did earlier. For 9, these are monomial denominators, so you just got to come up with an LCD that would work for both of them. I can turn each of the 8 and the 12 into a 24. So by multiplying by 3, for the first one and 2 for the second one. And I'll use y cubed because that's the highest power. So the second fraction will need a 2y. Okay, keep in mind that plus sign is binding it. There's no GCF in the top. You're done. I know we're about 30 minutes in, but going on to complex fractions. Complex fractions just mean fractions within other fractions. I actually don't do these steps. I'm going to do something different. I look at each of the fractions and I identify the LCD of each of those fractions. I then multiply each fraction by the LCD over 1. And then I reduce. So for example, 1/4 over 1/8. The common denominator between 1/4 and 1/8 would be 8. So I'm multiplying 8 over 1. And then I like to box in to think of these separately as 2 separate multiplication problems. In the first box, I can cancel the 4 with the 8 and get a 2. And so then in the whole top box, that gives me 2 all over 1, all over. In the bottom box, the 8s would cancel or reduce to 1, so that leaves me with 1 over 1. And what I want you guys to notice is that if everything's over 1, you can ignore that. This goes to 2 over 1, which is just 2. So here's how this works then when I throw in some variables. I look at the 2a and the 3a. The LCD that I would pick between those would be 6a. So I'm going to multiply each of these by 6a over 1. And now think of these problems as 2 separate multiplications. In the top box, I can cancel the 2 with the 6 and get a 3. I can cancel the a's. This leaves me with 3 times a plus b. All over. In the bottom, I can cancel the a's. I can cancel the 3 with the 6 and get a 2. Leaves me with 2 times a plus b. The a plus b's cancel, and that leaves me with 3 halves. Scroll down to 3. Now I have 4 little mini fractions. So between each of these denominators, 2, 4, or 2x, 4, and x, the common denominator among all of those would be 4x. So I'm going to multiply each of these by 4x over 1. Now treat this as 4 mini multiplication problems. In the top left box, I can cancel the 2 with the 4 to get a 2. Nothing else will cancel there, so this leaves me with 2x times x, which is 2x squared. Minus, because that's this operator. The x's cancel in the next box, so 8 times 8 is 32. All over. Bottom left, the 4's cancel. X times 1 is x. Minus, x's cancel, 4. Now we're at a place, just like earlier, where I look to factor and cancel. You'll notice I have dots in the top. X minus 4 is reduced, so this leaves me with 2 times x plus 4. Now if you look at number 4, I have what I like to call little floaters, where they aren't fractions. turn them into fractions. Put them over 1. So now when you look at each of the denominators, it's 1x, 1, and x squared. So the common denominator that I would use is x squared. Multiply each of these by x squared over 1. So the idea here, guys, is that I'm clearing out the fractions. And then I think of these, oops, let's undo those. I think of these as 4 mini multiplication problems. In the upper left box, nothing's going to cancel. That's okay. It still leaves me with something over 1 in the denominator, so that's where x squared comes out, minus, I can cancel some x's, which leaves me with a 2x, all over x squared, because nothing cancels, minus 4. Factor out of GCF, factor dots, my x minus 2's cancel, and so the answer would actually be x over x plus 2. I just boxed it because I ran out of room. So that's complex fractions. Now, there's actually one more day of notes after this. Solving fractional equations. Anytime we say equations, that means there's an equal sign. The first one we'll talk about are proportions. This is when you have a single fraction equal to a single fraction. When you have this, you can cross multiply to solve. So that's 3 plus 2d equals 6 minus 4d. Notice I distributed the 2 to each of those terms. Now you're just solving like we did in Unit 1. Equals 3/2, or 3/6, or 1/2. Now what you do have to be aware of is that when you get a solution, it needs to not cause any of the denominators to go to 0 in the original problem. The good news is if you plugged 1/2 back in for d, 2 times 1/2 is just 1, plus 3 is, well, not 0, okay? It's 4. So because of that, you're okay. You don't have to reject an answer. Now, for number 2, if I cross multiply, we get 20y minus 5 equals 30y. Subtract the 30, or subtract the 20, I should say, and then divide by 10. So y equals negative 1/2. And that's okay, because if I plug it back in, it's not going to cause the denominator to go to 0. So those are proportions. So now we come on to these equations that look a little bit different. So now it's not a single fraction equal to a single fraction. It's the sum of fractions equal to another one. What we're going to do is get a common denominator among all of them. So if I look at the c, the 3c, and the 3, I would say the common denominator is 3c. So that means this first fraction is going to get a 3. So I'm multiplying by 3. Second fraction's fine. Third fraction needs a c. This is what we get. Now the catchphrase I'm going to say is when the problem equates, you can drop the base. So I'm going to ignore this denominator, and I solve the numerator. So this is 3 plus 1 equals 2c. 4 equals 2c, so I can divide by 2. And c would equal 2. Now you always have to check to make sure that you don't get any zeros in the denominator. So if I plug 2 back in, it would be fine. In fact, the only value of c that I cannot have is 0. Coming on to the next one, I would say the common denominator would be 4k. So I'm multiplying by those. So then I can say when the problem equates, drop the base. And k equals 5. That's fine. I checked my solutions. We're good. The only value of k I really couldn't have was 0. Because if I plug 0 back in, it would go to 0. 5 would be fine. Okay. Going on to harder ones, like number 4. Look at this denominator. Wait, I feel like that's a typo. Yep, this is supposed to be a 5. Don't know where my 5 went. Okay, so I look at the denominator of x squared minus 25, and I think, okay, well, that's made up of x plus 5x minus 5. When it's set equal to 1, its denominator is just 1. So when I look at x plus 5, and then x plus 5, x minus 5, and then 1, I would say the common denominator, again, is 1 of each. So I would want both an x plus 5 and an x minus 5. So that means the first fraction would need an x minus 5 to it. Second fraction already has the common denominator. The last fraction would need both of them. Okay, so when the problem equates, drop the base. So now I'm solving the numerator. So let me just rewrite out what I have. And I might as well just multiply that out while I'm at it. Okay, got to FOIL this out. So that's x squared minus 3x minus 10 plus x minus 1 equals x squared minus 25. X squareds drop out. Okay, I would add the 11 over. And then divide by negative 2. So x would equal 7. All right, one more problem, and this would really be the end of a crash course of Unit 3. Working together problems. Just an application of what we've been doing. So suppose Huck can paint a fence in 5 hours. I'm going to write this off to the side as Huck is 1 over 5. So he's creating one fence in 5 hours. If Tom helps him paint the fence, they can do it in 3 hours. So that's them working together. Together, it's 1 over 3. How long would it take Tom to paint the fence by himself? So he's our unknown. So Tom is going to be 1 over x. So the idea of working together problems is that it's individual plus individual equals together. Here are my individuals. So 1 over 5 plus 1 over x is equal to 1 over 3. So now we're at a place where we're looking at this and I have to decide what a common denominator would be. I would say it would be 15x. So the first guy is going to need a 3x. Second guy is going to need a 15. Last guy is going to need a 5x. When the problem equates, drop the base. So I got 3x plus 15 equals 5x. And so x would equal 7.5. So I'll stop right there. That's your crash course in Unit 3. I have the notes key on WITS 2 for all the other problems in case we didn't do them in class, but I hope this video helps.